This video discusses Newton's law of cooling, which is an application of exponential equations. Newton's law of cooling states the temperature T of a heated object at time little t is given by T equals C plus T sub 0 minus C times e to the k times t power, where C is the constant temperature of the surrounding medium, T sub 0 is the initial temperature of the heated object, and K is the negative constant that is associated with the cooling object. So basically, this is the formula that is used when you take a hot pan out of the oven, you set it on the counter, it cools in the air because the kitchen is cooler than the 350-degree oven, and how long does it take to cool to a certain temperature? That's the idea of what's happening here. So we have an object that's been heated to 100 degrees Celsius. It is left to cool in a room that has a temperature of 30 degrees Celsius. After 5 minutes, the temperature of the object is 80 degrees Celsius. The first thing we want to do is use Newton's law of cooling to find a model for the temperature of the object T after T minutes. We'll round our K value to 5 decimal places. This is similar to what we do when solving variation problems. We're going to start with an equation, which is Newton's basic law of cooling, T equals C plus T sub 0 minus C times e to the k times t power. And we're going to plug in information that was given to us so that we can find our K value, and then we'll rewrite our equation including that value for K. So let's see what they gave us. They said that our object had initially been heated to 100 degrees Celsius, so that's our T sub 0. It's left to cool in a room that is 30 degrees Celsius, so that's our C value. After 5 minutes, the temperature cooled to 80 degrees Celsius. The 5 minutes, that's our time, little t. And our 80 degrees Celsius, that's our final temperature, T. We'll plug these 4 numbers into our equation and solve for K. That gives us 80 equals 30 plus 100 minus 30 times e to the k times 5 power. And we want to solve for K. We can start by doing a little cleanup. We can subtract the 100 and the 30 in parentheses. And we can also rewrite that exponent to a form we like a little better. Let's make that 5K. And now we're solving for K. K is located in the exponent, so we are solving an exponential equation. That means that we need to isolate the exponential base and then rewrite it in logarithmic form to solve. So isolating that e to the 5x, we'll start by subtracting 30. And then we'll divide by 70. That gives us 5/7 is equal to e to the 5k power. Now we'll rewrite it in logarithmic form. Since our exponential base is e, we need to use logarithmic base e, which is our natural log. So the natural log of 5/7 is equal to 5k. And then lastly, we want to divide by 5. You don't want to find the natural log of 5/7 first and then divide that decimal by 5, because then we'll be rounding upon rounding. So we get that k is equal to the natural log of 5/7 divided by 5. Now we're ready to plug it into our calculator and round. The directions told us to round k to 5 decimal places. We get k to be equal to negative 0.06729. We will now plug our k value, our T sub 0, and our C into Newton's law of cooling, and that'll give us the model that describes what's going on here. So that'll be T equals 30 plus 100 minus 30 times e to the negative 0.06729 T power. The reason that we plug in that initial temperature and the temperature of the room is because those two things are staying constant. What's varying for us is the final temperature and the time. Now we can clean this up a little bit. Let's subtract what we have inside the parentheses, and we get the equation T equals 30 plus 70 times e to the negative 0.06729 T power. We will use this equation to answer the questions posed in Part B and in Part C. Part B says, what's the temperature of the object 20 minutes after the fact? We'll round our answer to the nearest hundredth. So they're telling us to find the temperature, find capital T after 20 minutes. So we're plugging in 20 for little t. So that's T equals 30 plus 70 times e to the negative 0.06729 times 20 power. You can plug this all in your calculator at once. Just be sure that you have parentheses around this product in the exponent. And we'll round our answer to the nearest hundredth. We get the temperature to be 48.22 degrees Celsius. In Part C, we're asked, when will the temperature of the object be 35 degrees Celsius? Round our answer to the nearest hundredth. So this time they're giving us the final temperature desired, and we want to figure out the time it takes. So 35 degrees Celsius will be our big T. We'll plug in for big T and solve for little t. That gives us the equation 35 equals 30 plus 70 times e to negative 0.06729 t. We're solving for little t, which is located in the exponent, so we are solving an exponential equation. We need to start by isolating the exponential base, the e to that power, and then we'll turn it into logarithmic form to solve. So isolating the e, we'll subtract 30. And then divide by 70. That gives us 1/14 equals e to the negative 0.06729 t power. Now that we've isolated the exponential base, we're ready to rewrite it in logarithmic form. Our logarithmic form needs to match our exponential form, so this will be natural log of 1/14 equals negative 0.06729 t. And then the last thing we need to do to solve for t is divide. Since this is natural log, we can just type it in our calculator. We don't need to use change of base formula. T is going to be equal to the natural log of 1/14 divided by negative 0.06729. And we'll put this in our calculator, round to the nearest hundredth. We get T to be 39.22, and our unit is minutes.